This is Andrea Hendricks, and I want to talk to you about integer exponents and the quotient rule in section 4.2. In this section, we're going to talk about 0 as an exponent, negative numbers as exponents, using the quotient rule for exponents, and a combination of rules. In the last section, 4.1, we dealt with exponential expressions in which the exponents were just natural numbers, that is, numbers of the form 1, 2, 3, or so on, our counting numbers. In this section, we're going to expand our study of exponents to include integers, that is, a set of numbers that include the negative whole numbers and 0, and the positive integers or positive whole numbers. So the first thing that I want to do is to look at what it means to have 0 as an exponent. If you recall, first of all, an exponent means to indicate or to repeat the base, the number of times that's indicated in the exponent, by multiplication. But to repeat something 0 times would not make sense. So we need to look at this in a different way so that all of our rules for exponents hold true and so forth. So the first thing that I want you to recall is that anything divided by itself, except 0, of course, because you can't divide by 0, is 1. Do you remember something like 5 over 5 is 1, or 2a over 2a is 1. The other thing that we're going to use in conjunction with this is the rule from 4.1, the quotient property. That is that x to the m divided by x to the n is x to the m minus n. That is, to divide like bases, we subtract their exponents. So let's consider some expressions that have something divided by itself, like x squared over x squared. Well, we already know that x squared over x squared has to be 1, right, because it's something divided by itself. But if we use the rules of exponents, it has to also hold true so that all of our other definitions work. So if we look at it in terms of x squared over x squared, where we're dividing like bases, the rule is we keep the base the same, and we have to subtract our exponent. So that would be x to the 2 minus 2, which is x to the 0. Well, you know in mathematics that you can't have something equal to two different values. So what that means is that 1 must be the value of x to the 0. Here's another example. 5 to the 6 divided by 5 to the 6, well, we know that has to be 1 because it's something divided by itself. If we use the rules of exponents, 5 to the 6 divided by 5 to the 6th is 5 to the 6 minus 6, which is 5 to the 0. So here again, it must be true that something raised to the 0 power is equivalent to 1. You can check this on your calculator. If you do 5, exponent key 0, you will get 1. Common fallacy is to say that that's 0, but that is not the case. So this is our definition. For any non-zero real number, right, this does not work for 0 to the 0, because 0 to anything we would say would be 0. So it's a contradiction, so that's not something that we can talk about. But any non-zero real number, base a, raised to the 0 power is going to be 1. For example, 17 to the 0 power is 1. My high school math teacher used to do crazy numbers like 256 to the 0 power is 1, right? 1,233 to the 0 power is 1. Anything to the 0 power is 1. Let's look at some practice with these types of expressions and evaluate them. I pulled these from the page 257 in your textbook or the exercise set for section 4.2. So if I have 9 to the 0, well, 9 is a non-zero number, so 9 to the 0 has to be 1. Negative 4 to the 0, my base is negative 4. The base could be anything except 0, so it doesn't matter here that it's negative. It is still 1. Now number 5 is a little bit different. This is the opposite of 9 to the 0, so you can really treat this as like a negative 1 times 9 to the 0. So this would really be the opposite of 1, which is just negative 1. So if the negative sign is not in parentheses with the number, it has to stay in the answer. What about this negative 2 to the 0? Well, negative 2 to the 0 is 1. Minus 2 to the 0 would be minus 1. So negative 2 to the 0 is negative 2 to the 0 minus 2 to the 0 is 1 minus 1, or 0. 0 to the 10th over 10 to the 0. Well, 0 to the 10th would be 0, but 10 to the 0 would be 1. So 0 over 1 is 0. Number 17, 7 to the 0 plus 9 to the 0 would be 1 plus 1, or 2. So I really think the tricky ones here are to distinguish between the 9 to the 0 and the negative 9 to the 0. Now we're going to talk about negative integers as exponents. So this is what I mean when we have something like, what does it mean to have x to the negative 1 or x to the negative 2? Here again, it doesn't make sense to repeat the base a negative number of times, so we're going to have to make a definition so that all of our other rules will hold true. So let's start with this example, x squared over x to the third. And let's just go through this using the rules of exponents. So if I know that x squared over x to the third is really x times x over x times x times x. Well, there are some like factors that can divide out, right? X divided by x leaves a 1. Another x divided by x leaves a 1. So that result is really 1 over x. Well, let's look at it using the quotient rule that we just talked about. We have x squared over x to the third. Using the quotient rule, that would have to be x to the 2 minus 3. Well, x to the 2 minus 3 is x to the negative 1. Sorry, I don't know why that pointer is still there. X to the negative 1. Well, what did we just talk about? We can't have an expression that equals two different things, so that has to be true that x to the negative 1 has to be the same thing as 1 over x. And this is the rule that we're going to use for negative exponents. A negative exponent just indicates to do the reciprocal of the base to the positive power. In other words, what is your base? Your base is x. The reciprocal of that is 1 over x, but we'll raise it to the first power in this case. So here's our rule. For any non-zero real number, a, and any integer n, a to the negative n is 1 over a to the n. In example, 3 to the negative 2 is 1 over 3 squared. Okay? So don't try to make any new rules about this. The negative exponent only indicates to do the reciprocal raised to the positive power. I see a lot of students trying to make this like 3 to the negative 2, making it like negative 9. That is in no way what this is saying to do. I just have to use this rule and apply the definition. So if I use the rule here, 4 to the negative 3 would have to become 1 over 4 to the third, or we can simplify that further to be 1 over 4 times 4 times 4 is 64. A little bit tricky here, 1/2 to the negative 4. We'll talk about in just a moment a way that you can do that easier, but for the time being we're going to think of this as 1 over our base, which is 1/2, to the fourth, which is 1 over 1/2 to the fourth would be 1 over 16. And then you remember that when you divide fractions, you multiply by the reciprocal. So this is the same thing as 1 times 16 over 1, or just 16. If you remember the rule that I said, you're basically taking the reciprocal of the base raised to the positive power. Well, what is the reciprocal of 1/2? The reciprocal of 1/2 is 2. Then we can raise it to the positive power of 4. So 1/2 to the negative 4, a really quicker way to do that is to take the reciprocal of the base, raised to the positive power, and we'll get 16. Okay, but this is a long way to go about it. Negative 3 to the negative 4 would be 1 over our base, which is negative 3, to the positive 4. Okay, if the negative is in parentheses, it has to carry down to stay in parentheses in the denominator. So 1 over negative 3 to the 4th. So this would be, let me get this closed out here. 1 over negative 3 to the 4th would be 1 over negative 3 repeated 4 times is a positive 81. Now here's an example where the negative is not in parentheses, so this would be the opposite of 1 over 2 to the 4th, because if we deal with 2 to the negative 4, it's 1 over 2 to the 4th, and that negative sign carries over. So this would be the opposite, or negative 1 over 16. What about 1 over 2 to the negative 4? If we do it the long way, the 1 in the numerator stays. The 2 to the negative 4 is really 1 over 2 to the 4th. So we have 1 over 16, which is similar to number 21, because now we multiply by the reciprocal. 1 times 16 over 1, which is 16. Excuse me. Okay, I'm going to show you at the end of this lecture how you can use your calculator to check your work. So a negative exponent means to do 1 over the base to the positive power. Let's look at a few more rules that kind of come out from all of this. Here's changing from negative to positive exponents. The rule is for any non-zero numbers a and b, and any integers m and n, if you have a to the negative m over b to the negative n, you get b to the n over a to the m. Notice what happens. The a to the negative m goes to the denominator to become a positive power. The b to the negative n comes up to the numerator and becomes a positive power. A over b to the negative m is what I was talking about before. If you take the reciprocal of the base, and you can raise it to the positive power, that's what it means to be raised to a negative exponent. So the reciprocal of a over b is b over a, and we can change the power to a positive since we did the reciprocal. So let's look at this example. I'm going to show you the long way, but then I'm going to show you the shortcut so you don't really have to do this long way at all. If I have 3 to the negative 2 over 5 to the negative 3, the long way would suggest that I have to get rid of the negative exponents by using the rule. So 3 to the negative 2 is 1 over 3 squared. Well, then 5 to the negative 3 in the denominator is 1 over 5 to the third. Well, if we divide fractions, we multiply by the reciprocal. So this is really 1 over 3 squared times 5 to the third over 1, which is 5 to the third over 3 squared, or if we simplify that further, is 125 over 9. But you see how that rule that we talked about up there applied? What happened when we went through the definition? The 3 to the negative 2 had to come down to become a positive power. The 5 to the negative 3 had to come up to become a positive power. And that's really what happens in a fraction. If you cross the fraction bar, the power is the opposite of what it was. 2 over 3 to the negative 3. I did one earlier that was similar to this, but just to review it, that one way to look at that would be 1 over, sorry, this keeps coming up, 1 over 2/3 to the positive 3. So I can think of that as 1 over, what is that, 8 over 27. If we multiply by the reciprocal, it would be 1 times 27 over 8, which is 27 over 8. But if you remember what I said earlier, if you have a negative exponent, take the reciprocal of the base, so the reciprocal of 2/3 is 3/2, and the power becomes positive. So now if we cube 3/2, remember from the last section, that means the power goes to the numerator and denominator. We get 3 cubed of 27 over 2 cubed, which is 8. So it's a little bit easier to apply the reciprocal first and then change the power. Another rule that we used earlier in this lecture and also in the last section is a quotient rule. that a to the m over a to the n is a to the m minus n. Well, this rule is going to apply regardless of what m and n are. That is, they can be any integers. In the last section, we just looked at them being positive, where the numerator's power was larger than the denominator's. So just to review that at first, like 5 to the 8th over 5 to the 5th, they're like bases, so we can subtract the exponents to get 5 to the 8 minus 5, which is 5 to the 3rd, or 125. Another common mistake is to divide those bases, but remember that's 8 copies of 5 over 5 copies of 5. So when you cancel out those common ones, you still have 3 copies of 5 remaining. Number 33 has a negative exponent in the denominator. There's really a couple of ways that you can do this. One way is to think of that power in the numerator as being a 1. So if we apply the quotient rule, this would be 5 to the 1 minus a negative 1. Be very careful. The denominator's power is negative, so we have to subtract that negative number. And 1 minus negative 1 is really 1 plus 1, or 2, so that would be 25. Another way you can do that is remove the negative exponent. So if you want to, the 5 to the negative 1, by what we were just talking about, has to come up to the numerator to become positive. The numerator's power is already positive, so another way we could do this is 5 to the 1 from the numerator times, bring up the denominator's expression to make that 5 to the 1, and we still get 5 squared by adding the exponents. X to the 12 over x to the negative 3, very similar. That would be, by the quotient rule, x to the 12 minus a negative 3. So that's really x to the 12 plus 3, or x to the 15. Now I selected a few more from the exercise set just to review. 1 over 6 to the negative 3. We can do it in a couple ways. We can write that as 1 over 6 to the 3rd, which is really 1 times 6 to the 3rd over 1, because we multiply by the reciprocal, which is just 6 to the 3rd, or 216. Another way is just to bring up the 6 to the negative 3 immediately to make it 6 to the positive 3, and then you would get 216 initially. P to the 5th times Q to the negative 8, not really a whole lot to do there except to rewrite it without a negative exponent. And so P to the 5th is just itself. Q to the negative 8 is 1 over Q to the 8. Well, if we multiply these, think of P to the 5th as being over 1. So this is really P to the 5th over Q to the 8th. Again, just confirming what we talked about earlier, that if you have a negative expression, if you move it across the denominator, across the fraction bar, move it down, it's going to change signs to become positive. X to the negative 3rd y over 4z squared, or z to the negative 2 rather. The easiest way to do this is to use the rule about crossing the fraction bar to change the sign. So if we want to make all of the negative exponents positive, the x to the negative 3 will have to move, as well as the z to the negative 2. So the y in the numerator stays. The x to the negative 3 is going to come down to become x to the positive 3. The 4 in the denominator will stay, and the z to the negative 2 is going to come up to become z squared. Okay. Since the 4 is not in parentheses, it has to stay in its location. If that 4z were in parentheses, the whole thing would have to move up to become positive. A few more problems. A plus b to the negative 3 over a plus b to the negative 4. These are like bases, so we can use a quotient rule, which says this is a plus b to the negative 3 minus negative 4, which that's really negative 3 plus 4, which is 1. So this is just simply a plus b to the first power, or just a plus b. Okay. Number 60. Y to the negative 8 times y to the 5th times y to the negative 2. Now that we know how negative exponents are defined, any of those rules from section 4.1 apply. This is multiplying like bases, so the rule is we can add the exponents. So if we add the exponents, we would have to add negative 8 plus 5 plus a negative 2 Negative 8 plus 5 is negative 3, plus negative 2 is negative 5. So this is y to the negative 5. But we'll never leave a negative exponent. We would write that as 1 over y to the 5th. Number 63, we have a quotient to a power, so that exponent is going to apply to everything inside the fraction. So if we have x to the negative 1 raised to the negative 2, remember that rule. The power rule says we multiply the exponents to get x to the positive 2, then y to the negative 2, all over z squared to the negative 2 would become z to the negative 4. And then we don't want to leave these negative exponents, so we'd write this as x squared times z to the 4th over y squared. Okay? Now I brought a couple more problems on that are kind of basic, but where common mistakes are made. If I have 2x to the negative 3 and I want to rewrite that with a positive exponent, this 2 is not connected to the negative power, so this is just 2 times x to the negative 3, which is 2 times 1 over x cubed. If we simplify that, remember the 2 is over 1, so that's really 2 over x to the 3rd. Okay? Now negative 6 times x to the negative 1, same thing. We have negative 6 times x to the negative 1. Now I tell you, I see students confusing negative coefficients with negative powers. Negative 6 is negative 6. It can't be written any other way. But then x to the negative 1 can. So this is negative 6 times 1 over x. So if we multiply those and bring them together as one fraction, that's negative 6 over x. So notice our rule. It's okay. Or our rule is we have to have positive exponents. It didn't say anything about our answer being positive or negative. So it's okay to have a negative coefficient in that problem. The last thing I wanted to leave with you is how to use a calculator to check these negative exponents. Obviously this only works with numerical expressions, but if I wanted to check that 5 to the negative 3 was really 1 over 5 cubed, on the calculator you can enter 5 raised to the negative 3. Be sure that you use the negative sign from the bottom row of the calculator if you have a TI 83 or 84. In other words, don't use the subtraction sign for the negative. So if I do 5 raised to the negative 3 and enter, I'm going to get this decimal 0.008. But your calculator has the ability to convert that to a fraction. If you press the math key, which is on the second row, I think it's in green, and then 1, that should see something that looks like this, and enter, it's going to convert the 0.008 to the decimal equivalent or fractional equivalent, which is 1 over 125. Then you can check, is that the same thing as 1 over 5 cubed? And so if you enter 1 divided by 5 raised to the 3rd, you're going to get 0.008. It has the same decimal, so we know those two things are equivalent to each other. Okay? You can also do the 0 exponents and any of that on here as well. So I hope that helps with section 4.2. If you have any questions, you know what to do. Contact me. Thanks. Bye-bye.